Okay, let's take a look at a few examples from 4.3. We already looked at number 7, or at least something similar to that in the previous section, or the previous lecture, I mean. Let's go ahead and look at, let's try number 12 here. Number 12, we have a function f of x, and it's equal to x squared times e to the x. And we're supposed to, again, find the intervals in which it's increasing and decreasing, find local max and min values, and find intervals of concavity and the inflection points. So, first thing we're going to do is find the intervals of increasing and decreasing. So that, of course, means we're going to have to take a look at the derivative. F prime of x, well, we have ourselves a product here. The first function is x squared, the second is e to the x. So the derivative is going to be the first times the derivative of the second. Derivative of e to the x is e to the x, plus the second, which is e to the x, times the derivative of the first, which is 2x. Alright, so here's our derivative. Notice this function is defined everywhere, so we don't have any places, any critical values where the function is not defined. So we're just going to be looking for where does this derivative equal 0 to find our critical points. Alright, so we have e to the x. We're going to factor that out, actually, and it leaves me with an x squared plus 2x. So we're looking for where does this function equal 0. Well, two things multiplied together to give me 0 means one of those things has to be 0. Now, I think you guys know that e to the x can never be 0. No matter what you put in for the function, put in for x here, e to that power is never 0. Remember what e to the x looks like. It looks like this. It'll get as close as you want to 0 as x heads off towards negative infinity, but it'll never get there. So that means the only place we have a possibility of our derivative equaling 0 is where x squared plus 2x equals 0. So if I factor an x out of there, I have x times the quantity x plus 2 equals 0. And so either x is equal to 0 or x is equal to negative 2. So I have these two critical values, x equals 0 and x equals negative 2. So let's go ahead then and let's see, our derivative, as we said, was e to the x times x squared plus 2x. And so we're going to make the real number line here. And we had two values, negative 2 and 0, that were critical values. So let's look at f prime of x down here first. And let's start with f prime of, well, something to the left of negative 2, something in this region like negative 3. Well, that's e to the negative 3 times negative 3 squared plus 2 times negative 3. Again, all I care about is whether this is positive or negative. E to the negative 3, that's 1 over e cubed, that's positive. Negative 3 squared, that's 9. And 9 plus 2 times, and that's 9 minus 6. So this is all going to be positive times a positive is positive. So our derivative is positive here. What does that mean about our function? That means our function is increasing. Alright, our derivative, if we take f prime of 0, here we have e to the 0 times 0 squared plus 2 times 0. Actually, that's going to be 0, isn't it? Yeah, we knew that already. How about let's try a number in between negative 2 and 0. Like, actually, let's do a different color too here. Let's try f prime of negative 1. So just pick some value between negative 2 and 0 to see what's going on in this interval. That's e to the negative 1, that's going to be positive, times negative 1 squared plus 2 times negative 1. So that's 1 over e to the first, or 1 over e. Again, that's positive, that's all we care about. Plus times 1 plus 2 times negative 1 is 1 minus 2. So that's a positive times a negative. It's going to be a negative there. So the derivative is negative. That means the function is decreasing. Okay, now let's see, something to the right of 0, like 1. F prime of 1 is equal to e to the first times 1 squared plus 2 times 1. That's 1, well, that's just e. E to the first is just e. It's positive. Again, that's all we care about. 1 plus 2 is 3. That's also positive. So our derivative here is going to be positive. That means our function is increasing. So we can actually answer both A and B here right off the bat. Part A, we can see that we have f is increasing on the intervals. Let's see, where were we going up? Where the derivative was positive. Negative infinity to negative 2 and 0 to infinity. So negative infinity to negative 2 and 0 to infinity. F is decreasing on that middle interval, which goes from negative 2 to 0. We can also then answer part B. We had two critical points, negative 2 and 0, and so we can see that we're going to have a local, let's see, a local what? Well, if you look at our function here, it's going to kind of do this number, right? increasing, decreasing, increasing. So we're going to have a local max at x equals -2. Local max at x equals -2. We're going to have a local min that occurs at x equals 0. Now we should say the local min and maximum values. So we're going to need to take f of -2. F of -2 was -2 squared times e to the -2. -2 squared, that's 4 times e to the -2, or 4 over e squared. Alright, f of 0 is 0 squared times e to the 0. 0 squared, which is 0 times 1, which is 0. So we have a local max at x equals -2, and it's a local max of 4 over e squared. We have a local min at x equals 0. It's a local min of 0. All right, and you can graph that function to see and verify that that's the case. Now, part C, then we want to use the second derivative. We want to find the points of concavity. So remember, f prime of x was equal to e to the x times x squared plus 2x. And so f double prime of x, well, let's see. Here we're going to have, again, a product rule. So we're going to have the first function times the first times the derivative of the second, which is 2x plus 2, plus the second function left alone, times the derivative of the first, which is just e to the x. So again, this is equal to, if we factor an e to the x out here, there, and there, we're left with 2x plus 2 plus x squared plus 2x. So we have e to the x times, what do we get here, x squared plus 4x plus 2. Now we want to know where the inflection points are. Well, inflection points occur where our second derivative is equal to 0. 2x plus 2, x squared plus 2. I think I get everything right here. Again, the only possibility here is that x squared plus 4x plus 2 is equal to 0, since again e to the x can't be 0. Well, let's see, we're going to have to look at the solutions of this. It's not going to factor, so we'll have to use the old quadratic formula. The solutions are going to be negative b, that's -4, plus or minus the square root of b squared, that's 4 squared, minus 4 times a, which is 1, times c, which is 2, all over 2 times a, which is 1. So we get -4 plus or minus the square root of 16 minus 8, all over 2. So -4 plus or minus the square root of 8 over 2. -4 plus or minus 2 root 2 over 2. So we get solutions of -2 plus or minus the square root of 2. These are, again, our inflection points. Okay. Now what we can do then is we can see where we're going to be concave up and where we're going to be concave down for intervals of concavity and the inflection points. So here with our second derivative then, we can make a real number line, and over here will be -2 minus the square root of 2, and somewhere to the right here will be -2 plus the square root of 2. Now let's try and find some values we can test our second derivative. Remember what our second derivative is. Our second derivative is equal to, what's equal to? E to the x times x squared plus 4x plus 2. Those are our nicest form. Well, I'm going to let you guys do it from here. Basically, all you're going to do is you're going to pick some value from here and see if the derivative is positive or negative. Pick some value between these two values and pick some value over here. You might want to get an estimate of what these values are. I think this is going to be approximately -3.4, and this is going to be approximately about 0.58. Okay, so you might want to try something like 0 would be a good one to try in the middle. In fact, let's just go ahead and do that one. F double prime of 0, that's e to the 0, which is 1 times 0 squared plus 4 times 0 plus 2. You can see this is 1 times 2. This is positive. So the second derivative down here is going to be positive in this region. Positive. That means we're going to be concave up here. My guess is you might want to try something bigger than 0.58, like maybe 1 here and something like -4 here. My guess is we're going to be concave down here and here. Alright, let's try another example. Let's go ahead and just set up number 28. We may not go through the whole thing here, but we have a function f. It's a function of t, and it's equal to t plus the cosine of t. And we're also restricting t between pi and 2 pi. So t plus cosine t, but we're only allowed between -2 pi and 2 pi. So let's find our critical values first by taking the derivative. Derivative of t, well, we have 1. And so we have just, let's see, derivative of t is going to be 1, and then derivative of cosine is negative sine So 1 minus sine of t. Now this is defined everywhere, so we're just going to be looking for where it's equal to 0. Where does 1 equal the sine of t? The sine of t is equal to 1. Well, what does sine look like? Sine, you remember, looks like this. And like this. So this is at 0 here, and this is at 2 pi, and this is at negative 2 pi. So where does sine equal 1? Well, it looks like at two spots here, pi over 2, and back here at negative 3 pi over 2. So we're going to have 2 points, pi over 2 and negative 3 pi over 2. And that's what you're going to want to check then. So you're going to check negative 3 pi over 2 and pi over 2 to find where your function is increasing and decreasing. Remember, this is not your function. This is just the sine function that we used to solve when our derivative is equal to 0. Now, for the second derivative, we said f prime of t was 1 minus sine t, right? Because derivative of cosine is negative sine. Let's see what f double prime is. F double prime, derivative of 1, that's a constant, that's 0. Derivative of sine is cosine, so we have negative cosine t. So where is negative cosine of t equal to 0? This will give us our inflection points. That's where the cosine itself is equal to 0. And again, between negative 2 pi and 2 pi. Well, what does cosine look like? Cosine looks like this, where we have negative 2 pi here and 2 pi here. So where is cosine equal to 0? Well, cosine of pi over 2 is 0, cosine of 3 pi over 2 is 0, cosine of negative pi over 2 is 0, and cosine of negative 3 pi over 2 is 0. So you have those four places, negative 3 pi over 2, negative pi over 2, pi over 2, and 3 pi over 2 are your inflection points. So those are the ones you want to use to determine concavity. Alright. Alright, and then I think maybe the last one we'll look at is number 34. We'll see if we can get that one set up. It's a little bit more difficult. 34, we have the function f of x, and it's equal to e to the x divided by 1 plus e to the x. We'll look at a couple things. We want to first find the vertical and horizontal asymptotes. Now, remember that our horizontal asymptotes are going to be the limits as we go off to infinity. So, if we look at the limit as x goes to infinity of e to the x over 1 plus e to the x, one thing we can do here is divide everything by e to the x. So we'll say this is the limit as x goes to infinity of, so what I'm doing again is multiplying by 1 over e to the x on top and bottom. So that's just going to be 1 then on top, and I'm going to have 1 over e to the x plus 1. Well, as x goes to infinity, e to the x goes to infinity, so this is going to 0 then. 1 over something getting very big goes to 0, so our limit there is going to be 1. Now you can see the same thing is going to be true for negative. Oh, that's not true. That's not true. Let's look at what happens. If we take the limit as x goes to negative infinity of e to the x over 1 plus e to the x. Well, what's happening here? Well, as this gets bigger in the negative direction, this is heading towards 0. Both this and this are heading towards 0, because remember what e to the x looks like. Looks like that. So as we head towards negative infinity, the function goes to 0. And so we're just left with 0 over 1, or 0. Okay, so we have our horizontal asymptotes. Now the next thing we want to do is find our vertical asymptotes. For our vertical asymptotes, remember what we're looking for basically is where our function is going to be undefined. And so we're looking for where is 1 plus e to the x equals 0. Because that's the denominator of our function. That's where e to the x equals negative 1. And there are no such places where e to the x is negative 1. E to the x is never 0 and it's never negative. So we don't have any vertical asymptotes. There's no places where our function is undefined. Okay, let's find the local max and min values then. So we want to find now the local max and min values. And to do that, what we're going to do is we're going to need to take our derivative. So f of x is e to the x over 1 plus e to the x. So f prime of x is going to be equal to what? I don't know what that thing is there. Let's see, it's the bottom times the derivative of the top. Derivative of the top is just e to the x. Minus the top, e to the x, times the derivative of the bottom. Derivative of 1 is 0, derivative of e to the x is e to the x. All of that divided by the bottom squared. 1 plus e to the x squared. So what we have here then is, this is equal to, let's see, we have 1 plus e to the x times e to the x minus e to the 2x, e to the x quantity squared, over 1 plus e to the x quantity squared. Now again, the denominator is never going to be 0, so we don't have to worry about places where a derivative is not defined. We just need to worry about where the numerator is 0. So we're basically going to be setting 1 plus e to the x times e to the x minus e to the 2x equal to 0. So this is where 1 plus e to the x times e to the x is equal to e to the 2x. Right? Now what we can do here is I can divide both sides by an e to the x. The reason I can do that is because e to the x is never 0. So I can divide by that. And that's going to leave me with then a 1 plus e to the x equals e to the x. Subtracting an e to the x from both sides. And what do we get here? We get that 1 is equal to 0. Well, that's ridiculous. 1 is never equal to 0. So we have no critical points. Let me just double check what we did there. Alright, so I think that's true. So now we're going to look for inflection points. We have no critical points, so no local max and min values. So next thing we want to do is find inflection points. So that's where the second derivative is equal to 0. So we want to find inflection points. So let's go back to our first derivative. Remember what that was. That was, let's see if we can find it here. I guess right here. So 1 plus e to the x, or maybe we can use this one right here. 1 plus e to the x times e to the x minus e to the 2x. 1 plus e to the x. E to the x minus e to the 2x over the quantity of 1 plus e to the x squared. Now this is not going to be a very fun second derivative. Let's see if we can make it a little bit simpler. If I distribute that e to the x through here, oh yeah, I should have done this a long time ago. We have e to the x plus e to the 2x minus e to the 2x all over the quantity of 1 plus e to the x squared, so positive and negative of those, and we're just left with e to the x over 1 plus e to the x quantity squared. Now of course this can never be 0 because the denominator, well, because the numerator e to the x can never be 0. That's why our first derivative was never 0 and we had no critical points. Let's take the second derivative now. So we're going to have to use the quotient rule. It's going to be the bottom, 1 plus e to the x quantity squared times the derivative of the top, which is e to the x, minus the top, which is e to the x, times the derivative of the bottom. You have to use a chain rule here. That's 2 times 1 plus e to the x to the first power times the derivative of what's inside, which is just e to the x. All of that divided by 1 plus e to the x squared squared, or 1 plus e to the x to the fourth. Alright, so again, we're just looking for where our second derivative is going to be equal to 0. So let's simplify this a little bit if we can. If I FOIL this 1 plus e to the x out, I get 1 plus 2e to the x plus e to the 2x, all that times e to the x, minus e to the 2x when I took this one and multiplied together, times 2 plus 2e to the x. All that over 1 plus e to the x to the fourth. So let's keep going here, simplifying this. If I distribute the e to the x on the top, I have e to the x plus 2e to the 2x plus e to the 3x, right? Because you just add the exponents there, 2x plus x, minus 2e to the 2x minus 2e to the 3x, all over my denominator, 1 plus e to the x to the fourth, which I really don't care about because I just want to know where this is equal to 0. I'm setting this equal to 0. What do we have here? We have a positive 2e to the 2x and a negative 2e to the 2x. So I'm left with basically e to the x plus e to the 3x minus, minus 2e to the 3x. Where does that equal 0? That's where e to the x minus e to the 3x is equal to 0. Okay, so that's where e to the x equals e to the 3x. Dividing both sides by e to the x, I get 1 is equal to e to the 2x. Well, we're going to have a spot here. Where does 1 equal e to the 2x? Well, what power do I have to raise e to get 1? That's right, 0. So this would be x is equal to 0. You could also write this in logarithmic form. You could say the exponent on e to get 1 is 2x. The natural log of 1 is 0. So x is equal to 0. So this is our inflection point. Alright, so you could test then the concavity there by going to the left and to the right of that inflection point. And what you should end up getting then is that one inflection point at x equals 0. If we draw a graph of this thing, Here's what the graph looks like. E to the x divided by e to the x plus 1. Notice that we don't have any critical values. Any places where our derivative is equal to 0. The function is always increasing. The function is always going to be, well, the function itself is always positive, and the first derivative is always positive. Now, we do have two places of concavity. If you go to the right, if you plug a value in bigger than 0, remember we had a point of inflection at x equals 0. So anything to the right, we're concave down. So if you put something like 1 into your second derivative, you should get a negative value out. If we put something like negative 1 or anything less than 0 in, you should get a positive second derivative because we're concave up here. So it's concave up increasing, have an inflection point at x equals 0, and then concave down, but also increasing. Alright, so there is that one. And notice that the limit, our horizontal asymptote to the right is 1 and to the left is 0. No vertical asymptotes like we had established earlier. So we should be able to get a good sketch from, well, there is the sketch, but hopefully we can get that just from the information that we found. Alright, you should be in good shape then for your homework. Your password is pulchritudinous. Pulchritudinous. This is a good word here. It just means good looking. Possessing physical beauty. Pulchritudinous. Pulchritudinous. Good luck on 4.3. As I said, this is the last section that you'll need to worry about for Unit 3. There won't be any exam problems from 4.4. I'll send out an email about 4.4.